Hey there, everyone. This is a video specifically intended for Tuesday for the hybrid B and virtual only students. However, if you are a hybrid A student and miss school on Monday, you should watch this video too. If you are a hybrid A student and kind of got back behind, for whatever reason, this video will be helpful to you. So please feel free to watch it and use it. But what we're going to really focus on today is activity 8. And we're going to have a little bit of discussion, complete the intro at the beginning, and then also work on part B. Okay, so that's what we're covering today. At any point, please feel free to pause the video and so you can do some work. So if you haven't done so already, please open up your Google Classroom, and under Activity 8, there are two things that you need to open up. There is not that. There is a Google Sheet that you need to have open up, and this is what that first page looks like. And there's also some graph paper that looks like this that you need to open up. So if you get those both open, that would be fantastic. Okay, so let's talk about this activity. What you are going to be doing is you're going to be comparing the relationship between three different variables, and those variables are force, mass, and acceleration. And we've talked about all of those variables, but now we're going to see how they fit together, how they relate to each other. And we're going to do that by creating a graph. So before we jump into that, I do want you to look at I just moved this stuff around a little bit here. Okay. I would like you to look at this getting started box right here and answer this question. It says, what is the relationship between acceleration and changes in distance and speed? So there's really no wrong answer here. This is just getting your brains going and thinking today. But go ahead and answer this question to the best of your ability. If you're feeling really stumped, if it seems just a little too wordy, just focus on acceleration and speed. So how do you think acceleration and speed relate to each other? What do they have to do with each other? If one changes, does the other change? Okay, go ahead and pause the video and write down your answer now. Okay, so hopefully you have your definition written down. And the next thing is we are going to read the intro here. And I did set books out on your desk, so please feel free to use the hardcover book if it is easier for you to read that. And activity 8 is found on page 33. So either open that book or follow along here. And as always, just as a reminder, as we're reading this introduction, you should be writing down 3 key ideas or questions that you have in the notes section here in pink. So there are 3 blue boxes. You should have something written in each box. I'll be honest, the first paragraph, there isn't really a whole lot of information that I would probably pull out of that first paragraph. And if you find something, that's okay. But the majority of the information that you're writing your notes on is going to be down here in the second paragraph. Okay. So another idea that you might want to do is make your screen split screen so you can play this video on a small portion and then put your Google Sheet, this activity 8, open next to it. And so you can write then as the video is playing. Okay, so, okay, here we go. Follow along with what I'm reading and take notes. In the previous activities, you learned about force, mass, and changes in motion, both speed and direction. In this activity, you will further explore acceleration and then investigate the precise relationship between the mass of an object and the force applied to it, and the object's acceleration. You will consider how the relationships between these variables are important in a vehicle accident. Scientists describe speed in meters per second, m/s, and they measure mass in kilograms, kg. You will need to know the standard units used to measure acceleration and force. Acceleration is the change in speed measured in meters per second. Per unit time measured in seconds. So the unit for acceleration is meters per second, or m slash s. That's how it would be, meters per second per second. Or you can write that as meters per second squared. Force is measured in newtons, capital N. This unit is named after Sir Isaac Newton, a scientist who studied forces and motion. We'll learn more about Sir Isaac Newton next week when we're doing activity 9. Okay, so go ahead and take a second and pause the video, and you can jot down any other notes or key information in your pink boxes here. Okay, so now we have read our intro and we also have our key points pulled out of the intro. Let's talk for a second about the keywords. Big thing about the keywords is that my intentions for the keywords is I don't think you have to memorize a perfect worded book definition, okay? I know that you can Google all of these words and find a definition and then copy and paste that. That's not what I'm looking for. What I'm looking for when I ask about keywords is a working definition. That means if we're still working on it, it's still in progress, it's not finished, and that's okay. So these working definitions, I want them to be short and I want them to be simplified, but I want them to give me the level of understanding of how you understand what that word means. And I know that we've already seen some of these words before, and that's true because we will continue to see them throughout this unit, and I'm hoping each time that your definition of these terms starts to develop a little bit more and more. So, for instance, as I'm looking at this list, force is a really easy one, or not an easy one, but typically a really short one. If you're thinking for a second, like, how would I explain force? Even if you can't think of the perfect words to explain force, I want you to think possibly about, like, you could also give an example of force, okay? That could be fine too. But most often, we know that forces are going to, it's hard to find forces because forces aren't things that we can always necessarily see. but most of the time they are just classified as a push or a pull. So at least for 4s, all you'd have to do is put push or pull. Okay. So you don't have to do all of these keywords now. You do have to have them completed before you submit your assignment. But if you want to pause the video for now and just kind of write something down for each of these, that's fine. If you'd rather do that part tomorrow, that's okay too. Now, there is one change that I made because I had a typo. Your last word here, I accidentally put qualitative data. And I don't want to talk about qualitative data for this graph, but I want to talk about quantitative. So you hear the word quantity, and quantity means it's some has a numeric value. It's based on numbers. So changes to quantitative data. And then I also want you to add this definition that it's data that has numbers, and because it has numbers, we can graph it. So if you need to just pause the video, go ahead. If not, we'll keep moving forward. So last thing I want you to think about, the how graphs can be used to show motion. And we've already looked at some different graphs before, but let's consider these different graphs, because I know you're familiar with them. But we looked at graphs when we talked about Tisha and Josh heading to school. And if you don't remember, Tisha and Josh are next door neighbors, and they live at the end of the street that the school is on. So it's a straight shot for them. But try to think about, what did these graphs show us? What did they show us? Okay. So one thing that they showed us is I want you to think about these positive slopes. The positive slopes, the dot there is the dot. Oh man, I'm sorry. My brain is not working. Okay. Sorry about that. Let's talk about these graphs, what they're representing. So one thing that we look at are these positive slopes, and these positive slopes indicate that the person is moving away from their reference point, and their reference point is at home. So at the 0, at the origin, this is at home, and as we move away from their house, we can see that the slope goes up. Now, if the slope goes down and negative, that is when they are coming closer or going back home. Okay? Those are a couple things that you can tell from these graphs. What are some other things? Well, we can see how long it took them to go to school, because we can see the intervals down here on the x-axis. And then we can see how far it is, how far the school is from here. And sure enough, we can look at that on the y-axis. We can also tell when the vehicle stopped. We can tell the vehicle stopped because it's a flat line. So if you remember the story about Josh was heading to school until he realized he might have left his his homework, and then there is a flat line here, and that flat line indicates that during that time period there was no motion. He was staying in the same spot. So he couldn't find his homework, so he decided to drive back home. And so that's why this is going down. And then while he was at home, that's why there's a flat line here. He, sorry, I lost my train of thought here. This flat line is that no motion, that time is moving forward, but the car's not moving. So he's at home, he got his homework, and then he goes to school. Okay. So I just kind of discussed with you several different things about what those graphs showed you. Please make sure and jot down just a brief description of different things that that graph can show you. So go ahead and pause the video and write that down. Okay, let's go ahead and click on to the Part B tab. And we're going to skip over doing Part A right now, and we're just going to focus on Part B. And that's totally fine. We don't have to do this in order, those in order. But what we're going to do is find the mathematical relationship. So basically, we are going to create a graph that shows the direct relationship between force and acceleration. And it says that you may want to refer to the science skills student sheet 4 scatter plot and line graphing checklist, which is found at the end of the online textbook. So if you have the online textbook, or I mean, not the online, the textbook, the actual paper textbook, it's on page 88. And looks like this. Okay, you can also find this online on the online textbook. It's at the end. So if you go up to the category or the context, you can scroll down and find it. But that paper kind of will help you walk you through how to make a graph. Another thing I use though is I remember the word tails when making a graph because each letter stands for something. So, and as I go through, I'm going to follow tails. You can follow that way, or you can look up the line graphing checklist. Either way is fine. We're going to be using Kami to create our graph. And again, that graph paper is found in Google Classroom. Make sure that you are reading the directions in either with the textbook or the online textbook. So open up your textbook, and finally you're going to graph both experiment 1 and experiment 2 on the same piece of graph paper. So that is what we're going to kind of do to start out thinking about how to make this graph. So let's look at the steps here and here on the online textbook. Like I said, we're going to skip over part A, and so we're looking at part B. And the first thing for part B, it says, the table below shows precise measurements from an experiment in which a force was applied to pull a block along a frictionless track. And so this is the data that we're going to use here. So let's talk about what that actually means, that the data is what it's gathered, because you might not know. So a block, imagine a block of any sort, it could be a wood block, was pulled along a frictionless track. Now I know we haven't used a frictionless track yet, but a frictionless track is kind of like an air hockey table that it has air being pushed up and on it, and so items like glide all across it, because the air, since it's pushing up on it, um, there's no friction um, from gravity just pulling it down because there's air pushing up, and so it glides along without friction. And uh, but the force that's applied and then the acceleration that went due to a certain force. Now, force, it's hard for us to kind of think about what a force is. We know it's measured in newtons, but what the heck's a newton? So this right here is called a spring scale. And I don't know if you can see here, but there are like some numbers written down on the side here, and these represent newtons. And it's something, if I, pull something along or if something pulls down, there's a force being applied. So, for instance, if I pull on this and this little blue stopper thing comes down to, like right here, that is, I'm pulling down with 1 Newton of force. If I continue to pull down on it and make it go down here, now I'm pulling with 2 Newtons of force. And I can feel like I have to pull harder. So more than likely what they did to gather that information, they'd hook a spring scale to it. They'd use a force to pull it. And whatever force they were to pulling it, they could read it on their spring scale. And then the block would move. And as the block started moving, they found the distance it traveled and how long it took to travel that certain distance. So they calculated the speed. Because remember, we can calculate speed by saying distance divided by time. And so that would allow us to find how much it was accelerating over time. So that's what this information is saying. And we're going to see how, if we change the force, the amount of force that was being used, how it's going to change the acceleration. So that's what the information we're going to look at. Okay, on the next page, so, it says use experiment 1 data to make a graph of the relationship between the acceleration and force. Title the graph acceleration versus force. Label the graph. Label the graphed line experiment 1. Okay, so we're ready to start making our graph. And remember, you have that list that you can use, that scatter plot and line graphing checklist, and also this whole idea of tails we can also use. So the first thing in creating any type of graph is that we want to choose the appropriate title and the appropriate type of graph. Well, in the book, it already told us that the type of graph that we're going to make is a line graph because I was showing the relationship. The title, it just told us what the title was, is that you're going to title it acceleration versus force. So on your graph paper, go ahead and get that open. And using Kami, you can either write it on with your pen, or you can type it on with in your book there, but I'm going to go ahead and I'm going to title this Acceleration I'm having some problems writing this. Acceleration versus force. Hopefully yours is working a little bit better if you're writing it. So we already have T done because we know the type is a line graph and the title is acceleration versus force. Now, the next thing that we're going to look at is the A, which is variables on the correct axis. So we need to know which axis is which. And I don't know if you have a way to remember which axis is which, but we know we have an x-axis and we have a y-axis. So the way I remember the different axes is by just shaking and nodding my head. So if I think about X, if you have an X on a paper, or if you see an X like saying no, stop, or wrong, X in general means no. And if you shake your head no, like this, goes back and forth like this. So the x-axis is the horizontal axis. X means no. Y means yes. Shake your head yes. So this goes up and down. So Y is the vertical axis. So that's something that we need to kind of think about as well. But we know that down here as our x-axis, and over here is our y-axis. Now looking back at our directions, it does say hint. It says put the data for force on the x-axis and the data for acceleration on the y-axis. And so we just identified our different axes. So down here on the x, I'm going to write force. And of course, we measure force in newtons. So in parentheses, I'm going to write newtons. And on the y-axis, we said acceleration. And acceleration is measured in meters per second per second. Put that in parentheses. All right. So now we're ready to kind of think about the next step. Since we know our variables are on their correct axes, we're going to do the intervals. And intervals is how we're going to evenly space along the axes, okay? So we have intervals to do. We have to label the axes correctly, which we did because we it told us what to do in the directions. And then scale, just making sure that we're using the entire piece of graph paper. So on the next part, it says, discuss with your group why your graph does or does not indicate that there is a relationship between force and acceleration. And so we will know if there is a relationship if it creates a line. Once we plot our points, if there's a line that is created, that means that there's a relationship. If the points are just scattered randomly all over, that means that there won't be a relationship. So we're looking to see if there's a line. And it says use experiment 1 data and graph to determine the mathematical equation. Well, we're not quite there yet because we don't have it graphed yet. So let's finish graphing, and we need to come up with the intervals or the spacing. Well, looking back at the data table, we need to look and find the range. So what's our smallest number for each of the axes, and what is our largest number? We can see that in force, our smallest number is 2, and it goes up to 20. And our acceleration, our smallest number is 1, and it goes up to 10. Okay, so this is our x-axis. It needs to go up to 20, and our y-axis up to 10. So to find this, I first look at the number of lines I have on the bottom here, and I count those. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 does not go up to 20. So I'm going to have to rearrange my numbers a little bit because I have to be able to get up to 20. Well, if I have, I need to get to 20 and I only have 11 lines. So if I take, 11 is really close to 10. If I take 20 divided by 10, I get the number 2. So what that tells me is that I could, since if I only went up by ones, I'd only get to 11, and that won't work. But since 20 divided by 11, because 11 is so close to 2, I know, or 10, I know it's close to 2. What it tells me is I could go up by 2s, I could fit it all in there. So let me use a different color here. Maybe. Oh, it is just being, there we go. Okay, we'll use this blue color. Maybe. Man, I'm just having all sorts of issues. Okay, and I'm going to label my numbers here. So this would be 2. This is 4 newtons. This is 6, 8, 10, 12, 14, 16, 18, and 20. So I have the label, and remember our acceleration, its highest number was 10. Let's count these to find our range. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Well, that I can just go up by singles for the acceleration. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So there is our acceleration. Now we are ready to graph that. Our data from experiment 1. So if I come back here and look at the data table, so the first one listed, where I'll plot our points, is 4 newtons, and the acceleration is 2. So 4 newtons, and the speed or acceleration is 2. So I'm going to go ahead and put my first dot right there. Now you're going to graph the other 3 points. And the next one is 2 newtons, and the acceleration is 1 meters per second squared. So here's 2 newtons, and here's the 1. So this point goes right here. The next one is 20 newtons and 10 meters per second squared. So here's my 20 newtons, and if I go up to the 10, I'll be right there. And then our last piece of data for experiment 1, is 10 newtons, and the acceleration is 5. So here's 10, and I follow it up to the 5, and I put my line right there. And then I'm going to draw a line that best fits all those dots. So here's my line. I use the same color. And and look at that. That is awesome. My data goes through those dots perfectly. And don't forget, the last thing in the book, it said make sure to label this line that it's experiment 1, because you are going to graph experiment 2 on your own and put it on here. So I'm going to write experiment 1. Maybe I'll write experiment 1. Oops, I forgot to change it over to my pen. Although my pen has not been working great anyway. There we go. We can write right on the line that it's experiment 1. So, let's go I can get to. So then this is where it says discuss with your group. So this would be a great time if you're in class to pause, check and make sure on each other and make sure you made your graphs correctly, and take a second to discuss if it indicates that there's a relationship between force and acceleration. Remember, I told you the thing that we are looking at is that we were looking at if it would create a line, and that sure as heck created a line. So yes, there's a relationship between force and acceleration. Because as the force increased, what happened to the acceleration? The acceleration also increased. So now, if you're working with someone, you can discuss this and see if you can kind of come up with data as you're looking at the experiment 1 data to determine if there's a mathematical equation that shows the exact relationship between mass and force and acceleration. So record the relationships. It says record the relationships in your science notebook, so you can actually just record it on your paper there. So try to add, subtract, multiply, divide two of the measurements to see if you can get a third measurement. So, oops. So for instance, if I said, 20 and 10, how did those numbers relate? What could I do? So for instance, I could do, if I take 10 plus 10, that would be 20, right? Okay, so maybe I just need to add 10 to the acceleration and I will get force. Okay, well, it would have to work for all of them. So if I have 5 and I add 10 to that, so 5 plus 10 is 15. That would equal my force, right? Oh, wait, so that doesn't work. So is there the same equation that I could use for any of these data points that I would get a number? See if you can kind of come up with an idea with there. So pause, talk it over and discuss, and come up with an equation. Like I said, if you want, you can just kind of write your idea of your equation right down here in the corner. And then we're going to test that, whatever equation you come up with, against experiment 2. So step 6 says, the data table below shows an experiment for experiment 2. And it's saying, does your equation from step 5, what you just discussed and kind of came up with, does that equation that you just created work for this set of data also? If it does, go on to step 7. If it does not, determine the equation that works for the data for both expressions. So see if you can change your equation to see if you can get it to work. And then after you do that, so you can pause and do that, as soon as you're done, you're going to add the information from experiment 2, and you're going to graph this information on the same paper and go ahead and label it or experiment 2. So what I would do is I would choose a different color. So maybe, and then graph experiment 2 here. We'll do the first one together and then you can work on the rest. So here it says force is 4 and acceleration is 1. So I'll go back here. I'm going to find my force is 4 and acceleration is 1. So there's my first point. And then I would graph these other 3 and draw a line connecting your purple dots. So we'll just do one more. Let's do this. You have to do all 4 points, but we'll do, how about for the last one, force is 10 and acceleration is 2.5. So force is 10, here's a 10, and we would go to 2. Well, there's no 2.5, but we know 2.5 is halfway between 2 and 3, so it'll be right there. Put our dot there. Once you have all 4 points, you can go ahead and draw your line. And on your line, once you have your line, you will also label experiment 2. So I can kind of predict where my line is going to go right now, even though I don't have it all yet. Okay. So that's all you have to do. Hopefully that you can get through that. During Tuesday's class, like as long as you can get through graphing experiment 1, we're actually in really good shape. And then if you want to finish graphing the experiment 2 at home, that's okay. And then we will discuss it on Tuesday in class. Okay. So thank you guys so much for your hard work and attention. And I look forward to seeing you soon.